Hi, this is for Physics 305/395 at Cal State Dominguez Hills. A little supplemental video I'm making here with, it says solutions, really kind of comments on a partial solution for a text problem. It's everybody's favorite text problem so far, I think, the relativistic firecracker. The problem essentially is a relativistic firecracker. It's got V is 0.99 times the speed of light, explodes into two pieces, and the different parts, A, B, C, have different parameters. Find the energy of the pieces, actually. In part C, it just asks you about finding the energy of one of the pieces. I'm going to talk about the solution that I expected first, and then say just a few words at the end about a different way to do the same problem. And the different way is something that will lead you to hopefully better understanding later. A few things to note before I get really into the solution, and this is the kind of thing you should look for when you go to solve a problem. All these problems, parts A, B, and C, start with a decay that you can easily analyze in the center of mass frame. Maybe easily is an overstatement, at least for part C, but easier in the center of mass frame. But they ask about the energy in the lab frame. Okay, and you know, at least in principle, you should know, or at least know how to look up about velocity transformations via Lorentz. That was in your modern physics course. You should have known how to add velocities along a boost and perpendicular to a boost. You have a couple of formulas for that. I'll throw them in later. There are, as I noted, at least a couple good ways to do this problem. You don't necessarily need the velocity transformations. Finally, I note that energy and momentum conservation laws are good in any frame. So in principle, you could do this in the lab frame completely, except that I only told you about the kinematics of the breakup, that is how much energy goes to the masses of the decay products in the center of mass frame. So that prevents you from doing it easily, completely in the lab frame. So we're going to start by looking at the center of mass frame. Okay. In the center of mass, I've drawn a little diagram on the bottom of the page here. I've got a before with the firecracker sitting there, and it's sitting there in the center of mass. Of course, it's sitting still. And an after with two products going off to either side, and I've drawn it asymmetrically, even though for the first two parts of the problem it's symmetric. There's two cases, right? There's the symmetric case, the same mass products, which I could have done more easily than I do here. But then I've got the more general case of different mass products. And of course, the first one is really a special case of the second one. So I want to look a little bit at the second one, the general case, different mass products. So my generic two-body decay, and I've said this before in this class, and I think you may have run into it in modern physics. We like to work in units with c equals 1. So I'm going to do that throughout. And in fact, it will get me doing things like using beta and u for velocity interchangeably almost. Because if c is 1, then u over c, which is beta, is just the same value as u. So we're going to jump right into energy and momentum conservation. Okay. Energy before is energy after. The energy before in the center of mass frame is, as stated in the problem, the mass of the two decay products or pieces of the firecracker, plus 20% of the initial mass in the form of kinetic energy. It's also just equal to writing the energy momentum relationship for each of the decay particles. We've got the square root of m squared plus p squared, again, c is 1, for each particle 1 and particle 2. That's two different equations I've got there. Each of the line here and the line here equal to m0. Those are two different equations I can use. I've also got momentum conservation, which says that p before is p after, so in vector terms, 0 is the sum of p1 plus p2. And of course, what that really tells us is that there's only one absolute value of momentum for the decay products in the center of mass frame. And that is independent of whether the particles have the same size or not. I'm going to use the fact that I want to know energy for one decay product. This is really the trick of getting the asymmetric case. If I write the one equation that I had for conservation of energy, but I've now put that momentum is the same for both. My top line says m1 squared plus p squared and m2 squared plus p squared. So I have not assumed they have the same mass, but I have used, it's not an assumption, it's something I can use, that they have the same momentum. That momentum I can write in terms of e squared and m squared for the first particle and stick that in for the second. And I can say that the energy of the first particle, first being whichever one I want to consider in the asymmetric case, the light one, or either one in the symmetric case, I can do a little algebra with that, and I can find that the energy of this particle is given by a function of all the masses involved. Now, for my symmetric case, I can actually use that and say m1 is m2 and find out what I've got, and frankly, it's pretty straightforward. For my asymmetric case, where m2 and m1 are not the same, I'm going to get some function of the masses. If I know them as a fraction of the total mass, that gives me, using that relationship that I have 20% in kinetic energy, that gives me something that's just a function of the initial mass and m1 in the end, which is what I'm going to want for part C in the end. Okay, so in our symmetric case, I'm still in the center of mass frame, and the total energy for either of the particles is half of the energy I started with, which is the initial mass, times c squared, but c is 1. Okay, not a surprise. You could have said that right away without any of the algebra I already did. The easiest way to get speed is through the Lorentz factor gamma. Here on this page, and a little bit later, I've written gamma with a subscript u to remind myself that I'm talking about what happens for a particle. Because later I'm going to do a Lorentz boost and I have gamma corresponding to the difference between frames, speed of the original particle if you like, but it's the difference between frames, it's for a boost. Here I'm talking about for one of the decay products in a particular frame. Okay. So gamma, one of the relationships is that it's equal to the total energy over mass, and that's 1.25 in this case, because 20% of the energy went into kinetic energy and the other 80% went into mass. I can also write beta in terms of gamma, and again, beta and u are pretty much interchangeable here, and I get 0.6. So that tells me for all the cases in A and B, beta is 0.6 for each particle in the center of mass frame. For our cases, we've written v along z. That's the way I said to do it in the statement of the problem. So I can look up the formulas I know from modern physics about velocity addition with a Lorentz boost, and I get these formulas along the boost and perpendicular to the boost. When I actually do this, I'm going to treat the perpendicular case, part B, as though it's along x, because I don't care what you label x and y. Remember that for the perpendicular case, there's this factor of gamma of the boost. That's because of time dilation. It changes the transverse velocity. There would be another term if the velocity in the center of mass were not transverse, but had a transverse and a parallel component. But in that case, in this particular problem, you don't have any parallel component when you've got the transverse component, and the second term is going to go away. I wrote this just looking back at my notes for modern physics, so I have the c squareds in it. I want to remember to use c equals 1, so those look a lot simpler. The c's just drop out. Yeah. Now I'm pretty much ready to jump in and start doing things, at least for parts A and B. The particles have, as I stated, the same speed all the time. The frame boost in each, it corresponds to, I shouldn't really say is, but corresponds to a speed of 0.99 times the speed of light. So the Lorentz gamma factor, the Lorentz boost factor, is 7.1. So In A and C, u is along z, and in part B, it's perpendicular to z. Okay. For B, the transverse speed is actually lower in the lab frame because of the time dilation, but there's a forward component in the lab frame of 0.99. I said on the last one that I was going to start working. Well, let's actually do some algebra. I rewrite those formulas and I stick numbers in. I've got a plus or minus over here in front of the u sub z because I have both a forward and a backward particle. And I've only talked about the absolute value of the speed. I do need to take into account the direction. V is the speed of the relative speed of the frames, and I stick numbers in and I get these answers: 0.997 for the forward going particle and 0.961 for the backward going particle. Those are actual answers for speed, or speed over speed of light. In part B, the formula looks a little bit messier, but the z component, well, I wrote out a lot more than I really needed to. I've got zeros in there because the particle wasn't moving along z in the center of mass, but it reminds me that I do have the motion of the frame, 0.99. The transverse component, I've still got a zero in that one term in the denominator, but the gamma means that my transverse component of velocity in the lab frame is actually much lower than 0.6. It's less than 0.1 even. The total velocity squared, oh, and I'm sorry, I took the square root here. I should take the square root out of that, but I'm not going to re-record this. That should be u prime is the square root of uz prime squared plus ux prime squared, and that's what comes out 0.994. I did take the square root in that. Sorry about the mix-up on the formula written, but I'm going to leave that alone. That's not the answer to the question. The question asked for E, energy. Frankly, if you could do this, if you could get from the energy to the speed and then boost the speed into the lab frame, I think you can get from the speed in the lab frame back to the energy. So I think you can finish parts A and B there. Part C is a little more work, but you've actually got all you need for that as well. Everything's going to be in terms of the initial mass, because I never told you that. Part C is really mostly just like part A, but I also have a further parameter of the mass of the lighter particle. And I only care about the plus sign because in the statement of the question it says it's going forward. So you got enough to clean up here. It's not a lot different from what's already done. Now I want to go and talk about this other way to do the problem. When we solved the problem first in the center of mass frame, we got the energy pretty easily and then had to get the velocity. Space-time can be treated as a 4-vector. You should have done that in modern physics. If you hadn't, you can look at Appendix C1 of our class text, that is my notes, which are notes I made up for the last time, or one of the times I taught modern physics. You can actually, instead of writing the Lorentz transformations separately, you can write it as a big matrix. You don't get the velocity from that because velocity is not a 4-dimensional vector, and there's no natural extension to make it a 4-dimensional vector. With space-time, the 3 components of space corresponded to the 1 component of time, and you can put them together into one thing, a 4-vector. With velocity, there's nothing you can naturally do that with. But momentum always goes hand in hand with energy, and those can be made into a 4-dimensional vector in the same sense as space-time. Same sense means I actually can write a column vector or a row vector when I do different things, and I can write the matrix of my boost, and I could actually do boosts in all sorts of directions. And I could directly get, knowing the momentum and the energy in the center of mass frame, I can get it in a lab frame. I don't need to get the velocities first. So that would actually be easier. And later when you do problems, you might want to know how to do that. For now, let me just say this is like real-world problems with pions and other particles, and math doesn't care. Thanks. Bye.